Switching circuit with overcurrent protection. In integrated circuits, overcurrent protection is often included to protect the integrated circuits against excessive loads, such as short circuits at the output load, so as to prevent damage to the integrated circuit. Overcurrent protection can be implemented as a current limiting circuit or an electronic circuit breaker whereby, in response to a rapid increase in load current, the load current is either limited to a certain maximum level or the integrated circuit is shut off entirely. Overcurrent protection is essential for power transistors that are used in high voltage or high current applications to prevent damages to the power transistor caused by excessive load currents. In the extreme case of an abrupt short circuit or crowbar short circuit, a slow detection and protection response may allow excessive current to flow for an extended period of time, causing physical damage to the power transistor output device. Furthermore, slow detection and protection response to an overcurrent event can introduce undesired system issues. For instance, a power transistor is often used to drive a load from an input power supply, which is also supplying current to other circuitry within a system. If the load current becomes excessive and current limiting response is not activated fast enough, the supply voltage may be causing undesired system issues.
A power supply circuit includes an output transistor, including a source coupled to power supply voltage, and a drain from which the output voltage is outputted. A first error amplifier, powered by the power supply voltage and outputting a signal based on a potential difference between the output voltage and a reference voltage. A buffer transistor including a gate coupled to the output of the first error amplifier, and a source coupled by a constant current source to the power supply voltage and coupled to a gate output transistor. A current detection transistor coupled to the output transistor such that a gate and a source are shared. And an overcurrent protection circuit
includes an overcurrent protection circuit. The overcurrent protection circuit is the part surrounded by the dashed line in the figure. The overcurrent protection circuit is coupled to a drain of a current detection transistor TR3 and the gate of the buffer transistor TR2. The current detection transistor TR3, composed of a p-channel MOS transistor, is coupled to the output transistor TR1 such that a gate and source are shared. A resistor R11 is provided between the drain of the current detection transistor TR3 and the ground. A gate of a transistor TR11 composed of an N-channel MOS transistor is provided between the drain of the current detection transistor TR3 and the resistor R11. A drain of the transistor TR11 is coupled via a resistor R12 to power supply voltage VDD and at the same time to a gate of a transistor TR12 composed of a p-channel MOS transistor. A source of the transistor TR11 is coupled to the ground. A source of the transistor TR12 is coupled to the power supply voltage VDD. A drain of the transistor TR12 is coupled to the gate of the buffer transistor TR2.
When the output current of the output transistor TR1 increases, the drain current of the current detection transistor TR3 sharing the gate and source with the output transistor TR1 increases. When the drain current of the current detection transistor TR3 increases, the gate voltage of the transistor TR11 rises due to the resistor R11. Then, the on resistor of the transistor TR11 decreases and the gate voltage of the transistor TR12 lowers. Thus, the on resistance of the output transistor TR12 decreases, so that the gate voltage of the buffer transistor TR2 rises substantially to the power supply voltage VDD and the buffer transistor TR2 is turned off. Consequently, the gate voltage of the output transistor TR1 rises and the on resistance thereof increases, whereby the overcurrent protection works.